Hey there, my name is Alejandro, and welcome back for day 19 of me doing the NeetCode 150 challenge. So today we're doing a 1D dynamic programming problem because the topics between heap and 1D dynamic programming do not have any single easies in them. So like that backtracking doesn't have an easy and so on. So the very next easy is here, it's climbing stairs, 1D dynamic programming, and let's just get straight into it. Okay, problem 70, LeetCode easy. You're climbing a staircase, it takes n steps to reach the top. Each time you can either climb 1 or 2 steps, and how many distinct ways can you climb to the top? Okay, if there is one thing I remember, it's when I watched this a couple of years ago, because I was trying to learn what dynamic programming was. It's like, oh, what is this cool epic thing that everyone says is so hard and so on, da da da. I remember watching NeetCode's video on this and so on because I wanted to see what a DP problem was like. It's like, oh, it's just the Fibonacci sequence, and I didn't understand what the heck he was saying at the time, besides the fact that it's Fibonacci sequence. I was like, oh, okay, let's just do that and so on. But okay, so essentially, let me try to think about how to do this the DP actual way, right? So let's try to come up with a DP solution. So okay, essentially, I want to return. So if I have a memo, I essentially want the memo of n to return to me the number of steps it takes to get there, right? So maybe I do something like, okay, definite, we'll do top-down TP, self.memo is equal to an empty dictionary, right? And here we'll return self.climbstairs dp starting at n, right? So we want the number of ways it is possible to climb our stairs up to n, right? And so here, def climb stairs dp self comma an index I, right? So how many ways are there to climb the stairs at I, right? So first of all, if I is equal to 0, then we should return 0, right? It takes n steps to reach the tops. So if it takes, okay, let me think about this. Each time you either climb 1 or 2 steps, how many distinct ways can you climb to the top? What if you're already at the top, right? So okay, let me add a test case here. What if n is equal to 0? What is the expected? Here, let's just return 44, right? Something random. What? 4. What's going on? Return 5. What? Oh, n only has values between 1 and 45. Okay. Okay, so we cannot have... Okay, so 0 is not a value. What does 1 expect us to do? Is it 0? Is it 1? Okay, so it's 1. So there's one way to reach the top, which is by staying exactly where you are, right? So 1 should be equal to 0. Right? So how many... So, okay. If I is equal to 1, then return 1, right? So that's the idea, essentially. Or here I initialize 1 is to 1, and then I just do if I in self.memo, then return self.memo of I, right? Otherwise, we'll populate self.memo of I, and let's think about this. Okay, so 1 is a base case, which means you have already reached the top, right? So if you essentially get from 1, so the idea is essentially this, right? So we're gonna call, climb stairs at index I. So if I is the top, how many ways are there to reach it, right? So if I is equal to 1 already, then we've already essentially reached the top kind of thing and so on. So it's like, how many ways are there to reach I? Well, it's however many ways there were to reach I minus 1, right? As well as however many ways there was to reach I minus 2, right? Because if you're at step I minus 1, you can take 1 step to get to index I. And if you're at step 1 I minus 2, you can take a step of length 2, right? You can jump by 2 steps in order to get to I, right? So it's however many ways there exist to get to I minus 1, and however many ways there exist to I minus 2. Okay, so now this makes sense why this is related to the Fibonacci sequence, right? So if you're at step J, right? It's like the only ones you can reach from J are step J plus 1 as well as step J plus 2, right? So it's like if you're at an index I, how many ways exist to get to index I? Well, either you got there from index I minus 1, or you got there from I minus 2, right? So it's however many ways there are to get to I minus 1, as well as however many ways there are to get to I minus 2, right? And it's just, here's a base case that if like, okay, if we're calling this with position, you know, at 1, it's like, okay, there's only one way to get this case, so it's like our base case for the rest to be able to push on forward, right? So, okay, also, if I is equal to 2, I might need more than one base case, right? Because we always do I minus 1 or I minus 2, right? So if I do 2 minus 2 is 0, 0 is not valid, right? So if I is equal to 2, we can even just, you know, like, okay, n is equal to 2. What is the expected result of 2? Oh, 2 is 2, right? So the point is that, like, from 2, you're essentially able to, so from step 0, like you can either take 1 and 1, or you can take just 2, right? So here we'll have our basis case of 1 points to 1 and 2 points to 2, right? So those are our initial base cases, right? And everything else will fall into one of these two cases, right? So from step 2, there were 2 ways to get there, right? Or the point is that we can do something like 0 is colon 1. So you initially start at step 0, right? And so it's like, okay. You initially start at step 0, so how many ways are there to get to step number 1? Well, just one way, right? You take exactly one step and you're there, right? And then from 1, how many ways that were there to reach? Well, from 0 to 1, that was the only single possible one, right? But okay, maybe this makes more sense. So from 1, there was only one way. You exactly take one step. For 2, there are 2 ways. You either take 1 and 1, or you take just 2 directly from 0, right? So from 0, it's like there are 2 ways to get to a level of 2, but there's only one way to get to a level of 1, right? Okay. And now if I in self.memo return self.memo of I, otherwise it's how many steps. So to get to I, you either got there from I minus 1 or you got there from I minus 2. And so for each of those, you count the number of steps it took. So it's like, okay, self.memo of I is equal to self.climb stairs dp from I minus 1 plus self.climb stairs dp from I minus 2. And then here we return self.memo of I. So something like this I expect to work. Right, okay, and so let's just submit. Okay, and so yeah, this makes a lot more sense to me now that I like know dynamic programming, because I took like a advanced algorithms course and so on. Obviously, there's much easier ways to do this. Like I'm now realizing like, yeah, okay, this is directly Fibonacci and so on. I wonder if I actually would have come up, I would have thought of that myself and so on, maybe just from seeing this, but like, yeah, this is literally just the Fibonacci function. But the conceptual idea makes sense, right? So it's like to get to step number I, you either got there from step I minus 1 and took 1 step forward, or you got there from I minus 2 and took 2 steps forward, right? So really the number of ways to get to step I is the number of ways it takes to get from I to I minus 1, because then you could just go to I directly, or plus the number of steps that it takes to get to I minus 2, because again from there you can also take a step directly to I. So you essentially add those two together, and that's the number of ways you can get to step number I, right? But obviously we can do this a little bit more efficiently, because now we just realize that this is just Fibonacci, right? So here it's like, okay, this is our initial solution. Now realize this is just Fibonacci sequence. All right, so here we'll just do def climb stairs of this is now equal to just A, comma B equals 1, comma 1 for this in range n. A, comma B are equal to B A plus B, right? And it's like, what do I return? Do I return like A or something? Yeah, so that works, right? So yeah, and that's how you get to like the much more efficient solutions, right? So like if you submit a couple times, and there you go. Or actually n is equal to at most 45, right? So okay, I could actually do something kind of janky. Okay, let's do something kind of funny here. Okay, you guys are gonna be able to see. Climb stairs. Okay, so we'll do fib is equal to an empty array. Actually, we'll have 1 and 1 right here, and then while length of fib is less than 45, fib.append fib of -1 plus fib of -2. Fib. Okay. So now we can do something even better. Return this array at index n-1. Or am I not getting this right? Or just n? Okay. There you go. You can't do faster than this. Okay. Maybe I do. Fib.append fib. Okay, let's add this last number in there. Okay, there we go. Oh, what? We beat that much? Really? Or okay, maybe I define my this is my init. Self dot fib def init self dot fib is equal to this array, and I just return self dot fib of index n. Okay. Now I'm like, yeah, there you go, 87%. So I just pre-compute all the up to 45 elements of the Fibonacci sequence. Okay, well obviously this is just me being cheeky here. I'm not gonna actually do this. I'll just leave as my initial actual DP solution and so on. So yeah, this is a cool little trick, but okay, well, we'll just submit it this way and leave it as such, right? And yeah, so okay, 73% is actually not that bad, but okay. So as always, in all of these NeetCode 150 videos, I will do a quick recap of how I was able to solve the problem. So here, really, the idea that you have to realize is, okay, it's not immediately obvious why this is like equal to the Fibonacci sequence, but essentially it's like, okay, you want to get to the nth step, right? And you're always able to move by 1 or 2 steps, right? So you start at step number 0, right? So you start at step 0. And you want your end goal to be step number n, right? And so usually the way that it works with dynamic programming is you kind of want to like force subproblems, right? And the easy, good way to think about dynamic programming is like, okay, I just reached the final solution. How did I reach that final solution, right? So that's how at least my professor at the University of Toronto taught us like how to think about dynamic programming. It's always like, okay, I just reached the final answer. Let's think about how I got here, right? And often it's like, if you deal with an array of length n, it's like, okay, I was at step n-1. How was I able to like figure out how to get to step n, right? And so it's kind of like that. And so here, essentially, the idea is like, okay, if you start from the end, right? We just reached the nth step. What were the possible ways that we got to this nth step, right? And since you can only take 1 or 2 steps, the only possible ways were, okay, I either came from step n-1 or I came from step n-2, right? Because it's like I just reached step number n, right? And so since I can only take 1 or 2 steps, either I was at step n-1 and then took 1 step forward to reach step n, or I was at step n-2 and I took 2 steps forward in 1 move in order to get to step n, right? So that's very, very interesting. It's almost like we have a sub-formula for computing the number of steps that it took to get to step number n. So let's think about this. From step n, I either got there from step n-1 or step n-2. And when I count the number of ways that it takes to get to step n, well, since these are the only 2 possibilities, I can count all the ways that I could get to step n-1, and then it's like, from there I know I can directly get to step n, and then I can also count the number of ways I can get to n-2, and then for each of those ways, I could add 1 more step to get to step number n. So really, the number of ways that exist to get to step n is essentially the number of ways it takes to get to step n-1, because then you can jump directly to n, plus the number of steps that it takes that exist to get to n-2, because from then as well, I can also reach exactly the nth step, right? So essentially, I have a recursive subformula here where it's like climb stairs dp, where I represents, the ith step. How do I get to the ith step? Well, I essentially count the number of ways it takes to get to the i-1th step, because I could jump 1 from there, or the I minus 2 step, because from there I can also take a 2-step jump to reach that I step, right? So to get to step I, it's the number of ways I can get to I minus 1 plus the number of ways I can get to I minus 2. So that's essentially how you come up with the logic behind that solution. And for dynamic programming, it usually often helps, like, think of how did I get here? I just arrived at the final solution. How did I get here? And in this case, it's like, okay, I just arrived to a final solution where I just reached this step n. How did I get here? Oh, I can only climb by 1 or 2 steps. I was either at step n minus 1 or step n minus 2. Oh, since n minus 1, like, okay, if I compute all the ways that it takes to get to n minus 1, as well as all the number of ways that I can get to n minus 2, and add those together, then that becomes the number of ways I can get to step n. And since obviously these are both, like, you know, less than n, essentially I'm going to get down to a base case, right, where I'm either at, like, step 1 or step 2, which is why I put base cases for these two cases inside of my self.memo, right? So self.memo of I, essentially, all that represents is self.memo a value I, where self.memo is just a hash map, right? This just represents the number of ways I can reach step number I, right? And so here I have two base cases for step 1 and step 2. So let's think about 1, right? We start at step number 0. How many ways exist to get to step number 1? Well, there's only one way, right? You start from step 0 and you take one step forward to step number 1. Now for step number 2, it's like, okay, how many ways exist for that? Okay, well, I start from step 0. One way is I take one step and one step, and so now I'm at step 2. Or another way is I take 2 steps directly, and now I'm at step 2, right? So there are 2 ways to get to step 2 that are different, right? So these are essentially my base cases. And then when I do like n-1 and n-2 for any number that's bigger than that, again, I'm eventually going to reach those n-1 and n-2 base cases over here, right? But the only problem is, like, if I remove this, right, and I comment this out, this solution, by the way, it will still be valid. But yeah, exactly, I will time limit exceed it, right? So maximum recursion depth and so on. The reason we keep track of the self.memo is because there's a lot of computed work that happens in here, right? So from n here, I will have to compute the result for n-1 and n-2. But for n-1, I will need to compute the results for n-2 as well as n-3. And so here you can already tell that here I'm going to have to compute all the number of ways I can get to n-2, and here again I'm going to have to compute all the number of ways I can get to n-2, and for n-3 it'll also be like called a lot of times. In fact, there will be 2 to the n calls made in total, right? Because it's like from n I split into 2 different ones. For each of those I split into 2 different ones. So it will be like a tree of height n, a tree of a height n. Which will make 2 to the n total elements, so you don't want that. In fact, you can just make the solution from 2 to the n all the way down to O of n by just caching the results that you get. So this is called top-down DP, because we're using memoization, right? Whenever we figure out a result, we store it in our cache here and so on. So that way, whenever we call this function again, if we've already computed the, you know, like for example, in this case, like n-2, when we get to this n-2, we'll see, oh, that's already in my cache. I don't need to recompute the entire thing. I can just return whatever that result is that I found earlier, right? That way, the only calls we'll actually have to solve are like n-1, n-2, all the way up to 2 or 1 and so on, right? And so that way, it's like any other call that makes a call, we won't have to do the whole recomputation again, because it will be directly available in our cache as a result. Because again, if we recompute it, we'll get the exact same result. So we might as well store it once the very first time that we compute it, so that every time we need it again, it's already there for us to cache in O of 1 time instead of, you know, like the O of n time for that one specific branch, which would blow the problem up to an O of 2 to the n complexity. So if you've never seen this before, that's essentially why I'm doing it. I'm just caching results as soon as I compute their values, right? And initially for the base cases of 1 and 2, I have those pre-computed, because that way it's like when I go from n and, you know, I do n-1 and n-2 and so on, eventually I will hit one of these 2 base cases that I already know the answer for, right? It's just like basic recursion. But yeah, otherwise, I hope that explanation makes sense, and that's pretty much it for this video. As always, I will come here and make sure that I click the checkbox to say that I did this NeetCode 150 problem. In case you're curious and want to know the remaining schedule and upload dates for each of the problems that I will be doing for the rest of the challenge, I will have that down in the comment section below as a pinned comment for everyone to see. So in case you're curious, it's just there. But otherwise, that's pretty much it for this video. I hope that you guys find it useful or enjoyable in any way, shape, or form, and I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.